Hello, mathletes. Here we are taking notes on exponential functions and their graphs. So, exponential function, we're going to use our functional notation, like f of x, and then we have our argument here. So, just like any function, we're going to plug in whatever value we see here into any other x value we see on the right side. So, if we're evaluating f at 0, okay, it's going to be equal to 3 minus 2 to the negative 0. So any exponential function is going to have your variable as part of your index or in your exponent. So we can see 0 went into our exponent. So remember, anything to the 0 power is 1. So this is going to simplify to 3 minus 1 is 2. So we evaluated that function at 0. So on B, for f of 3, go ahead and plug that in. So f of 3 is equal to 3 minus 2 to the negative 3. Well, any negative exponent, I can write that as a reciprocal. So if this is over 1, I can write this as 1 over 2 to the third. All right? And simplifying this some more, I do 3 minus 1, 2 to the third is 8. So 1 minus, or 3 minus 1/8, I'm going to get a decimal of 2.875. Okay, so on this third example here, we're just changing our x value to a negative. So our answer is going to involve an x at the end. So if we do f of negative x, that's equal to 3 minus 2 to the negative x. So those negatives are going to end up canceling. So I get 3 minus 2 to the x. And that will be my final answer. I can't combine these because they don't have a common exponent or a base. So that is my final answer on here. So let's go ahead and look at our graphs here and how these functions are going to look as a graph. So we're going to look at the first just basic form, okay, of f of x equals 2 to the x. So you can see that our a value is greater than 0. So 2 is greater than 0, okay? And we can't let a be equal to 1 because if we just have 1, 2 powers, it's always just going to be 1. So we got to have something other than 1 to show growth or decay. So remember that exponents is repeated multiplication. So with repeated multiplication, the opposite direction is going to be division. So if we started at 2 to the first power, so our x is 1, it's 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. Okay? So noticing the pattern that it's doubling every time, in order to go the other direction, okay, notice that we're always just going to be dividing by 2. So 0 to the first power is 1. 2 to the negative 1 up here is going to be 1/2. 1 divided by 2 is 1/2. Dividing 1/2 again, you get 1/4, and then you get 1/8. Notice that these are just reciprocals because of our negative sign here. Okay, so if we graph this, okay, and we get these values at 0, 1, double it, 1, 2, double it, 2, 4, double it, 3, 8, and then half, half, and half. Notice if we keep taking half of these values, we're never going to be able to get negative because half of something is always going to be something, and we're never going to be able to go below our axis. So with our exponential graphs, we are going to get horizontal asymptotes, meaning that the graph will get so close to a value but never actually get there. So our horizontal asymptote here for this exponential function is where y equals 0. That no matter how many times I keep cutting this value, our y value, in half, it's never going to be negative because we're always going to have at least something left. It will get very, very close to 0, and that approaching to 0 is what we call a horizontal asymptote. Okay? So let's just look at some generalizations here. So we have two types of functions when we're dealing with exponential functions. One, when the graph is increasing, typically we call this a growth function. Okay, because our values are increasing as we're going from left to right. That happens when our a value is greater than 1. Remember, our a value is the base here, so we're going to keep multiplying. So if we multiply by anything greater than 1, it's going to get larger. So you can see in the green graph, it's 3 to the x. Since our base is bigger, it's getting larger faster. And since 2 to the x is smaller than 3, it's still getting larger, but not at a large significant rate as 3 to the x. So the other case is if we have an a that's between 0 and 1. Well, anytime we multiply by a number to 0 and 1, it gets smaller. Okay, so this is what we call a decay graph. That typically, when we're graphing things, we're talking about time here on our x-axis. Okay, but as we keep repetitively multiplying by 1/2, things are going to get smaller and smaller and smaller as we go off in that direction. Okay, same thing with 0.3. Okay, if we keep multiplying a value by 0.3, it's going to get smaller and smaller and smaller. Okay, so you can see it's a negative slope graph for decay, and it's a positive slope graph for growth. Okay, that's going to conclude our notes for tonight. Please come with any questions you might have next class.